Hi everyone, welcome back. This is Junior from Confluent. In this module, I want to talk about how compaction works in Apache Kafka. Well, most people may be mostly familiar with time-based retention in Kafka. In this case, you set up the cleaning policy to be deletion, and then you set an amount of time how long you want to keep the data in Kafka. Then, as those new log segments are generated, the oldest set of log segments will be deleted over time if they pass that retention time. Now, what's compaction? Compaction is a different way of retaining data. Instead of retaining data by time, it will be retained by key. Let's take a look at this example. In this example, all the records are published with keys. As you can see, some of the records, some of the keys are duplicated over time. So with compaction, you basically set a cleaning policy to be compact, and then what's going to happen is, over time, only the records with the latest record will be kept. If you have some older record with the same key, those will be garbage collected over time, like those in the pink. There's a special payload. If the payload is set to null, that's an indication that you want to delete this particular key. Then at some point, this is what we call a tombstone. It will also be cleaned up over time. So this is actually how the compaction works. It's a key-based retention. What are some of the use cases for compaction? It's actually a pretty useful concept. It's very useful to capture all those event changes for something that's updatable, like in the database table. For example, if you have a profile for all the customers, or you have a catalog for all the product descriptions, as those customer profiles and the product description changes, you may want to keep getting the latest changes of what's happening. But what compaction gives you is, in addition to keeping track with the latest changes, it can also bound the total amount of space that you need to store in this topic. Because over time, all the old records with the same key, they can be garbage collected. This is actually pretty useful for applications keep up with the incremental changes, but also do some bootstrapping occasionally. So in this case, let's say if you have applications starting from the very beginning, you may want to bootstrap its state by getting the latest value from all the keys, particular topic. You can do this by consuming from the very beginning of the offset in a compacted topic. And once this process is done, you can continue with newer changes to this topic. So it's actually a pretty convenient way of doing this kind of thing, because there's only a single Kafka topic you need to deal with, instead of having to have two systems, one dealing with bootstrap, the other dealing with incremental consumption. Now, let's look at how compaction works in Kafka. This is a compacted log. So over time, this compacted log will be divided into two parts. On the left side, these are the smaller offsets in the log. These will be the portion of what we call the cleaned log. In this case, in this portion of the log, there are no duplicate keys. All the duplicates have been removed. On the right-hand side, over time, these are accumulated dirty segments. This is the dirty portion of the log. In those segments, the data can have duplicates among themselves. They can also duplicate with some of the cleaned records as well. So the first step during cleaning is we have to determine a subset of those 30 segments to clean. The exact number of segments that you can choose depends on how much memory you have in the broker, and also how many keys you have in this particular topic. Once we have decided the segments to clean, what we'll do is we'll scan through all those selected dirty segments and then build an in-memory offset map. In this map, we'll be keeping the key as the key entry for the map, and for each of the key, we'll be keeping track of the latest offset we have seen for this particular key. This will be used for cleaning subsequently. After all the segments have loaded and then this offset has been built, we'll be going through the actual cleaning phase. In this cleaning phase, we'll be scanning from the very beginning of this log, including all those cleaned portions of the log and those previously loaded dirty segments. As we are scanning through each of those records, we'll be using the key in the record, do a lookup in this offset map. If the key is not present in the map, we know this record is still the latest for this key, and we'll be retaining this record. If this key is present in the map, we'll be comparing the record's offset with the offset stored associated with the key in this offset map. If the record offset is higher or equal, we know this record is still the latest record for this particular key, and it will be retaining this record. Otherwise, this record will be deleted. So once we know which records need to be retained, we'll be copying over those retained records into a new set of segments. When we are copying them over to the new segments, we'll be preserving the exact offsets of those records as they are in the old segments. This means between two consecutive records, there could be some holes in offset because some of the records in the middle could have been deleted. This is fine because the consumer application knows how to skip those holes in the offset gap. Once those new segments have been generated, we will be doing a swap of the old segments with the new one. Now, if you have a consumer that tries to ask for consuming some of the data within this offset range, they will be directed to the new set of segments. And over time, we'll be deleting the old segments. Once the cleaning process is done, we will also save the position, which is the offset of the last 30 segments we have loaded into the map, so that if the broker fails and start over again, it will be resuming the cleaning from this particular offset afterwards for subsequent cleaning. Okay, now let's take a look how we can clean Tombstone. This can be a little tricky because if we are not very careful, we can get into a situation where some of the delete records will never be propagated to the application. So this example shows this. So let's say we have this record at offset 50. This record is subsequently deleted because we have a key with a null payload at offset 57. So when we try to clean this segment, the naive way is we can remove both records at 50 and record at 57 because the key is subsequently deleted. But if we do that, it's possible for an application who has just finished reading the record at offset 50 and then took a pause. And then when it resumed consumption, it will no longer find the deleted record at offset 57. Then in this particular case, it just means this application will never realize that particular key has been deleted. Similar issue can happen if we are deleting a transactional marker too early. So in this case, for example, we have this record as part of transaction, which is aborted. And if we remove this aborted record and the transaction aborted marker together too quickly, then we can have the same situation where a consumer may have read this aborted record, but without reading the marker. So it doesn't know this actually is aborted. So to solve this issue, what we are dealing with the Tombstone deletion is we are cleaning that in two separate rounds. In the first round of cleaning, we will only remove the record at 50, but we'll leave the Tombstone marker at offset 57 as it is. When we keep it, we also set a time for when it can be safely deleted. And that time is set from the time when we clean the record plus a configured amount retention time. So the expectation is an application within this amount of time is expected to finish consuming all the way of this partitions data all the way to the end. So by retaining this data for long enough, now we will allow the applications enough time to finish resuming the consumption of this delete marker. And after that, we can safely delete the Tombstone. And we can do the same thing for the transaction marker as well. Now, when is compaction triggered? This is controlled with a few of the parameters. By default, we don't want the cleaning to happen too frequently because it can be resource intensive. So instead, what we want to do is to balance the cleaning with the amount of dirty data we have accumulated. So we'll be measuring how much additional dirty portion of the data we have accumulated and compare that over the total amount of data we have accumulated in this log. If that exceeded a certain threshold, by default it's 50%, then we will be triggering a cleaning. Some applications may want to defer the cleaning a little bit because they may want to see every record if possible. So in this case, they can set a minimum number of delay for compaction, and then the cleaning will happen after that. Some of the applications, they don't want to see duplicates too much, so they want to be able to clean the data as aggressively as possible. For them, they can also set a max compaction lag in this case, will be cleaning the data if it's older than this amount of time. To summarize, compaction is a very effective way of retaining the data by keys, and is very important for applications that want to keep track with updatable records by key. The guarantees we have when you use compaction is you are always guaranteed to see the latest record for a particular key, but you are just not always guaranteed to see every update of the record for every key. And that's it for this module. Thanks for listening.